So in this video, I'm going to talk about 3 precision position synthesis now of a path generator with prescribed timing. So we're going to really extend what we had done with a motion generator and say we're using the same equations, but now applying it to a path with prescribed timing. So what is path with prescribed timing? Remember, path generation, we're concerned about a point moving through space. We're only concerned about where is the coupler point. We don't care about the orientation of the coupler. When we add prescribed timing, we're also interested in what is the rotation of the input link as I go from the first position to the second and the first to the third. So that would be the prescribed timing piece. And ultimately what I've kind of sketched here on the screen is 3 precision positions as well as displacement vectors that describe the motion from, or the displacement from precision position 1 to 2 and 1 to 3. And then I've got the rotation of an input link, and I don't yet know where that ground pivot is. I don't know how long my W vector is or my Z vector. So that's what I'm trying to find out or trying to synthesize as part of this problem. So again, I'm going to look at a generic 4-bar. We're going to focus on one half of it primarily, but I've drawn it in position 1 and position J. So this is generic right now. Recognize we're focusing on 3 precision positions at this time, but later on we can extend it to 4 and perhaps even to 5. So when I've got these 3 positions, I'm going to say, let me start to develop these vector loop equations that I talked about before. So as I form the standard form equation from position 1 to 2, and again I'm focusing on just the W and the Z vector, I get this vector loop, and again where this comes from is that I'm going up the displaced position right here, W e to the I beta 2, adding Z e to the I alpha 2, subtracting off delta J, or delta 2 in this case, subtract Z, subtract W. I do a little rearranging and that gives me the form that I see there. I do the same thing from the first to the third position, which I don't have drawn here, just to the jth, but I think you understand that we can go to that third position. And then I get that second vector loop equation. Now, as I look at these and to say, let me compare this to the motion case I had before and consider how many unknowns, how many free choices do I have, I can look and say I've got, for prescribed variables, I've got the displacement vectors delta 2 and delta 3, and I've got prescribed timing angles, which are beta 2 and beta 3. So I've got 2 vector equations, which are the equivalent of 4 scalar equations, because each one has magnitude and angle or x and y components. And I've got a total of 6 unknowns here. My unknowns are the W vector, has 2 components, Z vector has 2 components, and then these 2 rotations of the coupler, alpha 2 and alpha 3. So I've got a total of 6 unknowns, 4 equations. I have to make 2 free choices to solve this system of equations. So to make this a linear system of equations, I'm going to do similar to what I did before, and I'm going to go ahead and pick alpha 2 and alpha 3. And once I do that, then it's just a linear system and I can solve for W and Z. Very similar to what we had talked about before, where I could use Kramer's rule or MATLAB. I put it in matrix format and I solve for W and Z. Fairly simple once we've learned how to do motion. Really path with timing is almost identical. And then we've solved for one half in our mechanism, the W and the Z side. Now, one typical thing to struggle with is, how do I synthesize the other half of my mechanism? What about the W star and the Z star? Do I solve those the same way? The answer is no. You do not solve them as though they were a path with prescribed timing. Think about what we just did here. We solved for W and Z, and now because we've done that, we have some rotation of my coupler, which we happen to pick because we picked alpha 2 and alpha 3, but I have that rotation of my coupler that goes from the first to the second position and the first to the third. But now this Z star vector, this is going to have to rotate by the same amount as I go from first to second and first to third if it's going to be part of that same coupler. So when we solve for W star and Z star, we actually treat these as a motion generation dyad. And what I mean by that is we have a prescribed displacement of the precision point, but we also have a prescribed rotation of the coupler. The coupler has to rotate the same amount as the W and Z that we just solved for in the first half of the 4-bar. Now when we solve the second half of the 4-bar, we have a prescribed rotation of our coupler. And if we're in 3 positions, we do free choices of the rotation of W star, that gamma angle. So a similar process to what we did for motion generation. So to create this full path with prescribed timing 4-bar, I synthesize one dyad of it, the W and the Z, with this path with prescribed timing method, and the other dyad as a motion generation dyad.